Okay, for the last part of this lecture, I'm going to introduce um, content on security risks of transportation systems. The main role of this part is the quantitative evaluation of the risk of a transportation network. But before that, I want to address five key common characteristics of transportation systems that have security implications. Okay, before that, okay, you may have noticed that today my PowerPoint is not in presentation mode. That's because I'm going to do calculations on slides, so it's more convenient to just show you each slides here without presentation mode, okay? So the first characteristic of transportation systems that is related to security is its openness and its accessibility, okay? Transportation systems, they are designed and organized for the efficient, convenient, and speedy, fast movement of large volumes of people and goods. Transportation systems must have a high degree of user access. This is actually the main reason why transportation systems are perfect targets for terrorist attacks, because terrorists always want more fatalities, okay, for a larger attention, more attention from the international society for political impacts, right? And the second characteristic here is extensive and ubiquitous. Transportation systems require vast amounts of physical infrastructure and assets. And most of this infrastructure is unguarded and sometimes unattended. Um, the reason could be that this infrastructure is automated, so you don't have to send people to attend to it. But sometimes it's about money. It's about investment because you have to send personnel to attend to it. Then you have to pay them, and there must be management of personnel. So a lot of extra resources for the infrastructure. Okay, so it can be attacked. Infrastructure can be attacked. And also the third characteristic here is that the emphasis on efficiency and competitiveness. Although much of the transportation infrastructure in US is owned by public sector, or say by government, okay, local government or federal government, the development of this infrastructure has been driven largely by the demands of private users, which means that efficiency is important. Okay, and some transportation systems, they are owned by private companies, which means profit is the first priority, which means that security is something distractive. Means that if you put more resources in security, you have to put less resources on profiting aspect of your company, of the system. Okay, so I have mentioned this multiple times that transportation security policies and measures, they are always crisis driven. Okay. The fourth characteristic here is the diverse owners, operators, users, and overseers. Okay, although the federal government helps fund construction, it owns and operates very little of this infrastructure. Most of it is controlled by thousands of state and local governments, which means that there are just so many stakeholders in this realm. Okay, they have different interests. Some of them are very wealthy, some of them are not that wealthy. So different people have different ideas. All this together makes transportation security policies and measures very hard to carry out, to implement. Okay, and the last one, intertwined with society and the global economy. So the characteristic 4 and 5, they basically means that transportation, there are just so many people they are involved. These people could be just real people or a government or different companies or government agencies at different scales. It's a very complex system. Okay, and now let's get to the main role of this part of the lecture, using traveler flow data to rank security threat. So here, in order to use this method, you have to accept an assumption that the higher the traveler flow, the higher the risk for a link or a node. Okay, because the larger the flow, the higher the flow, the higher probability that this link or this node will be selected as a target, right? And also, the higher the flow, the more difficult to manage, right? To manage a link or to manage a node in terms of transportation security. So here is a very simple transportation network with 1, 2, 3, 4, 4 nodes and 1, 2, 3, 3 links. And here is the table provided by this question. It's a table showing you number of daily flows between cities or between nodes. Okay, so we have figures and values here, and each one should be multiplied by 1,000 to address the real number of travelers. Okay, so let's read this table first. So we have multiple entries here, and each entry indicates the number of people traveling from an origin to a destination. For example, 7. 7 is the entry or is the intersection of A and B. And the first column here is for origins, which means that a node can be an origin or can be a destination. But the first column here indicates different origins. And the first row here indicates the row of destination for all those nodes in this network. So 7, what does it mean? It means that there are 7,000 people traveling from A, which is the origin, to B. Okay, so what does this 5 mean? It means that there are 5,000 people traveling from B to A every day. Okay, so each node can be an origin. It can also be a destination. And for some nodes, for example, node B, there are also passing through users, which means that some nodes, for example, B here, can also be considered as a transfer node. Okay, we'll talk about that later. But for now, let's just finish some calculations here. Because like I mentioned before, we assume that the level of risk is proportional to the users of a node or a link. So let's just do some calculation. For node A, it can be an origin, it can be a destination. So how many users are using A as origin, as an origin every day? How to calculate that? Of course, we calculate the sum of these 3 values. Because 7 is the number of travelers using A as origin and B as destination. 8 is the number of people using A as the origin and C as the destination. 3 is the number of people using A as origin and D as destination. So if you add them up, you have a value of people who uses A as origin. Okay, so you say, why is this empty? Because we do not consider the scenario that some people are using A as origin and also using A as destination. Okay, that's the reason why for diagonal of this table, we have empty entries, empty cells. Okay, so 7 plus 8 plus 3. What's the result? 18, right? So 18,000 people are using A as origin. So similarly, we can calculate this total number of people using a specific node as origin for B, C, and D. So for B, how many people are using B as origin? 17, right? So how many people are using C as origin? 19, right? And how many people are using D as origin? 11. Okay. And we can do this also for destinations. So how many people are using A as destination every day? So you calculate the sum of the second column here. So 16,000 people are using A as destination every day. Similarly, we have 21 for B, 18 for C, 10 for D. Oops, sorry. So now we have calculated numbers, or say the population, using all these nodes as origins and destinations. So for A, how many people are using A as destination and origin every day? How to calculate that? 16 plus 18, which is 34. So 34,000 people are using A as origin or destination every day. Okay, so another thing we need to consider here is that, like I mentioned before, some nodes can also be used as a transfer node, not only origin or destination. So for A, is there any passing through travelers for A? No, because A is a terminal of this network. You either start your travel from A, or you just use A as a destination. But B is different. If you want to, for example, if you want to travel from A to C, you have to pass through B, which means you also, these people who are passing through B, they're also using B, but they do not use B as origin or destination. And in this scenario, B is a transfer node or transfer station for those people who are traveling from A to C. Okay, since we're going to find out how many people are using all those nodes, we have to consider this scenario. Okay, so let's just calculate pass-through users at each node. For A, like I mentioned, there is no pass-through users. A is either an origin or a destination. So 0 people is using A for a transfer node. Similarly for C and D, they're all terminals, right? Okay, let's do not consider pass-through users for A, C, and D because there is no pass-through users. But B is different. If you're traveling from A to C, you are going to use B as a transfer node or pass-through node. If you're going to travel from C to A, still you need to use B for pass-through. Similarly, from A to D, you need to use B. From D to A, you also need to use B. From C to D, you need to use B as a pass-through station or a node. If you travel from D to C, still, right? So if you are a traveler using, using these routes, one of these routes, from A to C, from C to A, from A to D, from D to A, from C to D, or D to C, you are going to use B because B is unavoidable. B is the central node of this network, right? So we have to consider all those users using B as a pass-through node. So how many people are traveling from A to C? How to find that? So from A to C, so 8, right? From this table, we can find out that value. It's 8. 8 indicates the number of people who are using A as origin and C as destination. This is exactly the value we need for this entry because we want to know how many people are traveling from A to C. And if these people are traveling from A to C, they are going to use node B. Okay. Similarly, how many people are traveling from C to A? These people, they are also using B. So from C to A, also 8,000 people. So from A to D, 3,000 people. D to A, D as origin, A as destination, the intersection is 3. C to D, intersection is 1. D to C, origin is D, destination is C, so 4. So totally, how many people are using B as a pass-through node? So 8 plus 8, which is 16, plus 3, 19, plus 3, 22, 23, plus 4, 27. Okay, so 27,000 people are using B as a pass-through node. Okay, so using these two tables, we have calculated the number of people who are using these nodes as origins, destinations, and pass-through nodes. Okay, later we're going to evaluate how many users are using each node totally. Okay, let's just put all those nodes aside for now. Now let's talk about links. Not only nodes have risks, each link, each transportation link also has risks, okay, depending on how many users are using it. So we have 3 links here, right? Link AB, link BC, and link BD. So link AB, link BC, and link BD. Okay, so when we're talking about link, what do you think? Does direction matter? Of course it matters, right? So how many users are using link AB? When we're using AB as the name of the link, direction doesn't matter, right? Link AB is also link BA. But when we are trying to calculate the number of users, direction matters. Because if you want to travel from A to B, you are going to use link AB, right? But if you are trying to travel from B to A, you are still using link AB. So link AB as a name has nothing to do with directions. But when we're talking about travelers, number of travelers, the direction matters, because if you're traveling from A to B, that's one route. If you're traveling from B to A, that's another route. You have to consider users for both directions. Okay. So if you're traveling from A to B, you use AB. From B to A, you still use AB. What are other options here? If you're traveling from A to C, you need to use AB, right? You have to travel from A to B, then to C. So if you travel from A to C, you're traveling from A to C, you are going to use AB. If you are traveling along the reverse direction from C to A, you also need to use AB, right? But this time is actually traveling from B to A, but yeah, still link AB, right? So what else? If you are traveling from A to D, you need to use a link AB. If you're traveling from D to A, you're still going to use link AB. Is there any other route you're going to use? The question is wrong. Is there any other route including link AB? No. If you're traveling from D to C, you don't use AB. C to D, no. B to D, no. D to B, no. So we have exhausted all possible routes who include link AB. Okay, so you need some patience. You need some patience to exhaust all possibilities here. Okay, that's the only difficult part about this type of quantitative evaluation of transportation security using traveler data. So now you have exhausted all possibilities of routes who are using link AB. You need to find out how many users are there for each route. So how many users are there who are traveling from A to B? From A to B, 7. How many users are there from B to A? B to A, 5, right? How many users are there from A to C? A to C, 8. C to A, origin C, destination A, also 8. A to D, only 3. Oops, sorry, 3. And D to A, 3. So totally, how many users are there for link AB? How many people are using link AB? We add them up, of course. So 7 plus 3 is 10, 15, right? 23, 31, 34. Okay, so similarly, we can calculate how many users are using link BC and link BD. So for BC, of course, if you travel from B to C, you use it. Travel from C to B, you use it. AC, CA, DC, and CD. Is there any other possible routes using link BC? I don't think so. Okay, so let's find out associated users. Okay, BC, 6. CB, 10. AC, 8. CA, if I remember correct, yeah, 8. D say from D to say 4. From say to D, only 1. Okay, so together we have that's a 10, 20, 28, 36, 37. How about BD? BD. So travel, of course, travel from B to D, from D to B, right? A to D, D to A, C to D, D to C. Okay. So how many from B to D? B to D, 6, right? D to B, D to B, 4. A to D, 3. D to A, D to A, 3. C to D, only 1. D to C, D to C, 4. Okay, how many people are using BD? 10, 16, 17, 17 plus 4, 21. Okay. Okay. Now we have everything needed for risk evaluation for these nodes and links. For nodes, we have users using them as destinations, and we also have a number of users using them as origins. We also have number of users using them as pass-through nodes. Some of them are 0, but yeah, we have specific values for users using them as pass-through nodes. And we also have number of users using all 3 links. Okay, you may have noticed that I marked different values with different colors, so it's easier to differentiate. Okay, next, we need to make 2 tables, one for nodes, another one for link. So for each node, it can be an origin, it can be a destination, it could be a pass-through node. So we want to know in total how many users are using each node. So let's just check if we did the right calculation, okay, for originating or origins, 18, 17, 19, 11. Yep, we did it right? So 16, 21, 18, 10. Yeah, also correct. You just copy and paste, right? For pass-through 0, 27, 0, 0. 0, 27, 0, 0. Yep. So for links, 34, 37, 21. 34, 37, 25. Okay, everything is correct right now. So you just need to, for nodes, just add them up. So 18,000 people are using A as origin. 16,000 people are using A as a destination. 0 user is using A as pass-through. So together, how many people are using A in total? 18 plus 16. The result is 34. Do this for the rest nodes, 65, 37, 21. You can see the busiest node here is node B. It makes sense because it is the central node of the network. So now we have total users for each node. Okay, and like I mentioned before, the higher, the more the users, the higher the risk. So who has the highest rank for risk? Of course, node B, because it has the highest number of users. So, and then what's the second place? Who is the second place? Is node C. 37,000 people are using it. Third one, rank 3 is what? Node A. Then D has the lowest risk because least users are using D compared to A, B, and C. Okay, so this is the rank you want. Okay, also let's talk about links. Links are easier because we don't have to consider originating, arriving, or passing through. No matter you're using it from one direction or to another, just calculate, just add users up. Okay, so for AB is 34, for BC is 37, BD is 21. You can say that BC link BC is the winner. It has the highest risk among three links. Okay, then we have link AB, then link BD. So this is the final results you want, right? Because we wanted to evaluate risks and rank them for nodes and for links. And in the exam, there will be at least one question about this method. Okay, and in the exam, for each security threat or security risk ranking question, there will be multiple sub questions. For example, I would ask, how many users are using A as origin? Of course, the result is 18, but simply giving me 18 is not going to get you the full credit. You have to give me the calculation specific process. So you should write down 7 plus 8 plus 3 equals 18. Okay, that's a perfect answer for this sub question. Okay, and maybe another question is that how many users are using link AB in this transportation network? Then you need to show me all those routes, including link AB. So you don't have to make a table because the exam will be through Carmen. You cannot make a table in Carmen. Just list all those routes, AB space BA space AC space CA space AD space BA. This list here lets me know that you actually know how to find out, how to exhaust all possibilities of routes, including link AB. And then you can just use a new row to just write down associated users for each route, which means that in the exam, I'm not going to let you finish all big tables like this. I'm going to ask you to finish calculations for a specific link or for a specific node. Okay, because if you know how to do this calculation for a node or for a link, then you know how to do the calculation for all of them. Then ranking them is not a problem at all. So in the exam, please show me your results, but more importantly, show me how you found out this result. Okay, how many people are using link AB? Possible routes AB, BA, AC, CA, AD, DA. List them, and then give me the numbers of users for each route, 7588833. And after that, simply give me the result, which is the sum of these numbers, right? Similarly, if I'm asking you to find out how many users are using B, okay, then you should find out how many users are using B as an origin, as a destination, and as a pass-through. Okay, because I did not ask you how many people are using B as origin or as destination or as pass-through. I asked how many users in total are using node B. Because B can be an origin, can be a destination, or can be a pass-through node. So you have to calculate all those users using node B and give me a final result, which is 17 plus 21 plus 27. The result is 65. Okay, since there will be a question on this, and I know if you have never used this before, it could be a little bit tricky. You have to be patient. Okay, you have to do some very simple but important calculation, because if you did the wrong calculation for B as an origin, you will not get a correct result for the number of the total number of users for node B, because you did a wrong calculation, right? So you need to be careful. You need to be patient. Okay, and show me your results and your process of calculation. Right. So for B, how many users are using B as origin? So 5 plus 6 plus 7, that's the result. How many users are using B as a destination? 7 plus 10 plus 4. How many users are using B as a pass-through? For that specific question, you have to show me these roots. Okay, who use B as a pass-through node and give me associated data and a result. Okay. Okay. There is another example here. Okay. I will just leave it to you. I will just leave it to you. You can say here that the shape of the transportation network has changed, right? For the example I just showed you, there is a central node here, B, right? But for this one, there is no central node. Okay, let me finish this part of the calculation at least. So 7 plus 3, 18, right? So 14, 18, 13, 17, 20, 16, 10. Okay, so you can say for link users, it's a little bit more complex, especially for BC. Okay, for link AB, people are traveling from AB or from BA, from AC, CA, AD, DA. Okay, all those users, they are using link AB. BC is more complex, right? Because BC is in the middle of this network. So this link can be considered as a central link. So BC, CB, of course, if you travel from A to C to A, you also use link BC, right? B to B, B to D, D to B, okay? Also A to D, D to A. So here is the result. Okay, and for pass-through nodes, so A cannot be a pass-through node because it's a terminal of the network. D cannot be a pass-through node because it's another terminal of the node. These they are more complex, right? They're more complex. I have listed all results here, but I suggest using this table here to finish your own calculations first, and then compare your results with the key here, and say if you did it right. Okay, so the shape of the network matters, because the shape of the network, the topology of the network decides how many users are using each link here, and how many users are using nodes as pass-throughs. Okay, in terms of origin and destination, they are given by this table, right? So you don't have to worry about this part. You just need to calculate them, calculate sums. Okay, but when we're talking about links and pass-through nodes, you have to check the specific topology of the network. Okay, so yeah, another slide for the rankings. You can find them here, and also there is one more example from the real world, right? several big cities along the east coast of the United States. So northeast corridor of Amtrak serving Boston, Providence, New York City, Philadelphia, Baltimore, and Washington, D.C. So now we have 1, 2, 3, 4, 5, 6 nodes. Although, yeah, the topology of this network is very easy. It's just a linear network. But you can say it's much more complex as the number of nodes increases. So in these two examples, we only have 4 nodes, but here when you increase the number of nodes from 4 to 6, you can see how big the table is. And it's more difficult to exhaust all possibilities for roots. Of course, the calculation is more complex. So in the exam, do not worry about this. I will not give you 6 or 7 nodes to calculate. Maybe 3, maybe 4 would be good enough because it's just an exam. But you should also know it could be very complex to evaluate risks of nodes and links in real world. Okay, this is just a linear system, right? In the real world, if you consider all those smaller cities, the topology of the network will be extremely complex. And if that was the scenario, you cannot use your hand and brain to just exhaust all possibilities. You have to use a computer to do that, right? And I have shown you the calculations, the results of this real world transportation network using these two slides, and a third slide for ranks. Of course, I think you can just challenge yourself because I did this by hand. Okay, you can just erase or cover all those results. Just use this huge table to finish all those calculations and say if you are still if you're still standing there. Okay, after exhausting all possibilities correctly. Okay. So yeah, that's all I want to introduce today. You can see that we did some mathematics today for the evaluation of risks for transportation nodes and links. And this is actually the only lecture of this week because last year when the class was in person, I used another lecture of that week to do in-class practice with students. So I showed them this network and this network, and I gave them time to practice. And we will then go through all these questions together to make sure everybody knows what he or she is doing. Because there will be this type of question in the exam. But now we're totally online, so I would just give you time, the rest time of the week, to practice this type of question, okay? Using this transportation network and another one, a real world one, okay? I have provided keys for them, so be patient, sit down, get a pen, do some chart rating and graph rating for transportation networks. Okay, if you have any question, just email me. Okay, but I don't think there will be questions because the form of this question is just straightforward enough. You just need to be careful and start from this table given by the question and calculate sums. It's always sums, add up. But I think the most tricky part is exhausting all those roots for links and exhausting all those roots for nodes who are considered through pass-through nodes in the network. Okay, that's all I want to say for this week, actually. So do some practice, please do it, because in the exam there will be only 80 minutes. You need to be quick to finish all those questions. Okay, so be familiar with this type of problem or question. Okay, thank you.